Can I request Debasis Sengupta from the Indian Institute of Science to give the next talk on gaps in measurements in the Indian Ocean?
Yes, good evening and good morning. I'm going to try and share screen. If that does not work, Mani, I will request you to.
Yeah, sure, Debasis.
So I try share screen and then. No, Mani, I'm afraid I'll need your help with this. It's
okay. We are able to see your screen now.
You're able to see the screen.
Yes.
But I had my PowerPoint open and it doesn't work now.
Okay. Can I share screen from my side?
Yeah, please, and please.
Okay, sure.
Yeah, this has happened in the past. I apologize. I'll stop sharing so you can share, Mani. Yeah. Thanks, Mani. Can you all see the screen now? Mani, if you could make it big, yeah. Can we see the screen? Everybody see? Yes. All right. So thank you for having me on this meeting. And I loved Eric's and Craig's talk. It was so nicely put. In the beginning, Mani also mentioned that we have a data gap in the coastal, a serious data gap in the coastal regions, North Indian Ocean. So I want to illustrate that through a science problem that has been gaining a fair bit of attention in the last 10 years or so. Mani, the next slide. Yeah, so the ocean is stratified both by salinity and by temperature. This is an example of what happens when a very powerful tropical cyclone moves over the stratified ocean. The top panel shows what happened to the sea surface salinity. So by how much it changed, you can think of PSS as grams per kg. The mean for seawater is 35. So you can see how much the salinity changed along the track of this storm Irma. The bright red colors are about 1.5 or 2 grams per kg. So what the storm does, it mixes up the ocean, accesses the saltier water below, and so the satellite begins to see now that the surface has become saltier. In the same way, it accesses the cooler water that lies deeper down in the subsurface ocean. And this it does by turbulent mixing of the upper ocean. In some cases, in these powerful storms, the turbulent mixing goes down to more than 100 meters. So these are called thermal and haline wakes. So these brilliant new satellites that can see salinity of the ocean from space, they've kind of led to a revival of interest in what happens to the ocean salinity when a storm passes by. But also people are beginning to think of how the ocean itself influences storm intensity. And very briefly, the way that might work is, imagine you have, as very often happens in the tropics, you have a thin layer of fresh water. Eric alluded to this in the Bay of Bengal, that comes from the rivers or from rain. And in the top panel, you can see the storm has crossed the Amazon or Orinoco plume, fresh water that comes out of South America. And that's where the salinity gradient between the surface layer and the subsurface layer was larger. And the change in salinity as the storm breaks through that layer is also larger. Very often in the tropics, I was saying, there is this thin layer of fresh water. Underneath, there's a deeper layer of warm water. So in other words, the halocline is shallower than the thermocline. When that happens, the ocean can break through this shallow density stratification associated with the fresh water. But it only mixes up warmer pre-existing water, and therefore sea surface temperature does not cool. In this example of Irma, sea surface temperature cooled. These blue colors are 1 and 2 degrees Celsius. Closer to the US mainland, it may be larger, 2 degrees Celsius. And those two thin black lines are the radius of maximum winds associated with the storm. Next, please, Mani. So from the same study, we should look at the sources of data. One is the salinity satellite that I mentioned. And second are Argo floats, which Craig also mentioned and Eric mentioned in his talk. Argo floats go up and down in the ocean and give you profiles of temperature and salinity. So that second panel below, Mark B, is what is the salinity gradient, the vertical gradient of salinity in practical salinity scale per meter, gram per kg per meter of depth. So you can see the first of all, you can see the Amazon plume of South America. You can see the Bay of Bengal, Ganga, Brahmaputra, Irrawaddy, and you can see off China, the major rivers coming in. And these are exactly the places where, as shown in the top panel, once a cyclone passes by, and this is an average based on about 900 cyclones in these 10 years. And the data is taken from the salinity satellites called SMOS and SMAP, written down below. Those are also the places where the salinity changes the most in response to a passing tropical cyclone. Next, please, Mani. So this is again from the same study. They're looking at if the halocline is, or the base of the fresh layer is shallower than the base of the warm layer, then, as I said, the storm might break through the shallow layer. These cyclones have very strong, very powerful mixing effects. But it may still bring up only warm water. So in the presence of what is called this deep warm layer, barrier layer, the sea surface temperature cooling due to the cyclone can actually be reduced. And if you look at the two panels down below, C and D, you can see that if the barrier layer thickness is small, then the sea surface temperature cooling is large, and the x-axis is radius of maximum winds in terms of radius of maximum winds. On the right side, panel D is if the barrier layer thickness is larger than 5 meters, and sometimes it can be 30-40 meters in the Bay of Bengal, then indeed the sea surface temperature cooling in response to this storms is smaller. So that permits the storm to reach its potential intensity, because what cooling of the sea surface temperature does is it reduces the supply of moisture and heat to the storm. Therefore, if you have this barrier layer structure, the cyclone can reach closer to its potential intensity, because the sea surface temperature does not cool that much, or does not cool at all. In some cyclones in the Bay of Bengal, hardly cools at all. Next, please. Yes, so here are some slides that Dipanjan put together for 4 very powerful cyclones that passed over the Bay of Bengal. So the colors are sea surface height as seen from satellite. The vectors are velocity derived from the sea surface height using the relation between Coriolis force and pressure gradient. and only the large current vectors are shown, I think greater than 0.3 meters per second, 30 centimeters per second. So you can see the eddies. If you look at the left-hand panel, the track of the Odisha supercyclone 1999 is shown in green dots. This happened in late October, and you can see the East India coastal current that Eric was talking about in those black arrows hugging the coastline of India. And you can see that the eddies where the sea surface height is low, in the blue colors represent low sea surface height. Those are in the blue colors. This cyclone did not pass over a significantly strong eddy. It hardly led to any cooling of the sea surface temperature. This 1 degree cooling along the cyclone track could be explained simply by evaporative heat losses. There was another cyclone that Eric and Dipanjan studied very closely. It was Phelan, 2013, again October. In the open ocean, it did not lead to much cooling. Similar reasons as for the super cyclone. There's a layer of fresh water, then there's a layer of deeper warm water below. So the storm might mix up the ocean, and it does indeed mix up the ocean. The pre-storm mix layer depth was about 10 meters. It went to 40, 45 meters. And nothing much happened to the sea surface temperature. But in the contours here, the white contours, as it approached closer to the Odisha coast, where it finally made landfall, the temperature cooled by 1 degree, and that inside contour is 3 degrees. So question is, did the storm, it took about 6, 12, 18 hours to cross this 300 kilometers. Did the storm really lose intensity as it passed over this eddy-like feature and as the SST cooled? We don't know the answers because there are no observations there. More examples in the next slide. Two other cyclones. 2014, there was a powerful cyclone Hardar. That seemed to have led to some cooling in the open ocean as well. Again, near the coast, there's a 3 degrees Celsius cooling contour in white. And again, since there was no data, we don't know what happened there. Another tropical cyclone, Titli, October again. There is a 3 degrees Celsius cooling in association, roughly in the same location as this low sea level eddy-like feature. Once again, we do not have sufficient observations to understand what really happened there. And these are things of science interest, of course. There are many things we do not understand about air-sea interaction in tropical cyclones, but this is also of direct applied interest. Next slide, Mani. Yeah. So this is what Dipanjan did. He has made this diagram based on all the available Argo floats in 3 different winters, November to February, of the 2015-16 winter, the next year and the next year. The first year tracks are all in blue. The second winter tracks are all in red, and the third winter tracks are all in green. There is a fair number of Argo tracks in the open ocean, but see how few there are in very important places like the northern Bay of Bengal. There's just one Argo float in the North Bay of Bengal off the Bangladesh coast. There's one off the Myanmar coast shown in red on the right-hand side of your figure. And there's one in blue, dark blue, that was closer to the coast of India. So this situation is not optimal. We do need more measurements within that 300 kilometer distance from the coast that Mani was talking about in his introduction. So my conclusion slide, I've tried to write down some of these things. SST cooling, sea surface temperature cooling due to vertical mixing under storms is inhibited if a salinity stratified layer lies above a warm barrier layer. And there are 2 reasons for this. One, because you have to supply potential energy to break through that salinity stratification. And then the water underneath is very often warm. and then you're only mixing up warm water with the surface water. If the sea surface temperature does not cool, surface energy flux may remain high for long as the cyclone travels over the ocean, and that favors cyclone intensification. There's an increasing literature on this now, looking at the role of salinity on cyclone intensification just in the last 3 or 4 years. So we do need the basic measurements in the regular measurements in the exclusive economic zone for the coastal region close to Indian coast, the Myanmar coast, Bangladesh. Very, very important for countries in this region, for science as well. There could be many more measurements in the atmosphere itself from aircraft and so on, which I have not even mentioned, but surface pressure, winds, surface waves, salinity, temperature, ocean currents ought to be monitored in the data sparse coastal seas. So I'll stop here. Thank you.
Thank you, Debashish. I think after this talk, we had a short break for discussions. So we could probably take a few questions, either from any of the first 3 talks. Are there any questions?
Senator sir, I have a doubt in that. Can you hear me?
Yes, Cindy, I can hear you.
Yeah. That one plot you are showing about that cyclone delta salinity variation. No, that barrier layer thickness, if it is low, the salinity variation is higher. You are shown.
Can we go to the slide, Mani?
Yeah, I'm trying to go to that slide.
One with category 4, 5 written on it. I think that's the one. It's
one slide which had both temperature and salinity.
4 slides back, I think.
Yeah, just give me a moment.
Yeah, the 4th slide. The 4th.
Is this the one?
Yeah, that is the one. So you are shown that if the barrier layer thickness is low, the SS variation is less, and temperature is higher.
That's right. Yeah, the temperature cooling is larger in the absence of a barrier layer.
Okay, so salinity variation is vice versa. Is the opposite.
And if the barrier layer thickness is large, if the barrier layer is deep, then the temperature cooling is smaller.
Yeah, temperature part I understood, that salinity part is the one I am confused.
I see. So that's what you're asking. Category 4, 5. So the way I understood this is the storm just breaks through that shallow stratification and reaches deep down where it accesses the saltier water. So the strongest storms might change salinity by 0.3 or 0.4 parts per 1,000. All right. So that's and this is from a combination of Argo floats and satellite data. And remember, this is a mean picture. So in individual cases, you can have much larger changes in salinity and temperature, or much smaller changes in temperature as well. This is for all those 900 storms in 10 years that Rule and others looked at.
Yeah. Okay, thank you, sir.
Are there other questions? Okay, so we will have more opportunity in the rest of the week and on Monday next week for more discussions. Thank you, Debashish. And we could continue with the next talk.
Dr. Mani?
Yes.
I'm audible, Venkatesh here.
Yes.
Yeah, I will add to what Devashish has mentioned about observations requirement in the coastal region. This is a big topic being discussed in both UNESCO, IOC, Intergovernmental Oceanographic Commission, as well as the World Meteorological Organization. I'd like to share the larger level discussion where the member countries are involved. In the case of IOC, the discussion is on how do we make them to collect data, and also next is on the sharing part, which is really within the EZ, data sharing is a big issue over there. Even though it's very clear in the case of meteorology as well as SST, subsurface and other component is still a big question mark. In the case of World Meteorological Organization, it is moving towards a Congress. Is an important decision is called GBON, Global Basic Observing System, which is part of our which they needed to have for the terrestrial. I'm part of a committee there, the ocean component also being advocated. So if that comes through 2 to 3 years down the line, at least a basic data collection on temperature and pressure, this is what is being required now, would be talked about it in the many countries. I can also share with you that there are 25 island nations which are directly affected by any of the discussion what we have on the ocean disaster or a climate or a weather forecast. You'll be surprised not even 6 have got sustained observation. So this is the current scenario. 50% of the earth is covered by EZ, unless this is looked upon. Even if you look at it in our own Indian Ocean, 25 nations, not even more than two digit, less than 2 digit, less than 9, or that type of observation only are happening. This is what, in the larger perspective, we are discussing. In fact, day after tomorrow, we are having a meeting of GRA, Goose Regional Alliances. Currently, I'm the chair there. We are trying to work, but this pandemic has put a lot of question mark on the funding. Yes, science is driving that. I'm sure that these are all small nitty-gritty things. This is what in the UN decade in 2030 aiming to achieve that. I'm sure that this will succeed in the days to come. Thank you.
Thank you very much, Dr. Venkatesan. That's a very helpful input. So maybe we can proceed with the next talk by Professor Bharat Govindarajan at IIT Madras on unmanned aerial systems. Bharat?
Thank you. Yes, just 1 minute. Hoping you can see my screen. Okay, I'm hoping you can see me and hear me. So, good evening / good morning, everyone. And I'm Bharat, and I'm here to talk to you, slightly switching gears, and talking to you about the role of unmanned aerial systems for oceanography methodology. This is a collaborative effort, and I just have the opportunity to present what we've been up to here at IIT Madras on this front. I think the introduction is fairly clear. I don't think this audience needs one, but the idea is quite simple. We just want to obtain the atmospheric profiles as you see surface temperature in the Bay of Bengal. So this is as part of the Geophysical Flows Lab. So this is our task, particularly in phase 1. And it has, we want to better understand the atmospheric events, the response to the ocean, system data assimilation, and model calculation to sort of help with the other scientists. The image on the right sort of captures, in essence, what we like to do. So shown here is a close-up from the Bay of Bengal of coast of Visakhapatnam. The idea is, what if you could have an unmanned aerial vehicle sort of go through this pre-described trajectory, and at a particular altitude, you can cover an area, a predefined area, and go on collecting this information through various instruments on it. Right? So, of course, you have conventional techniques, and as already been alluded in previous talks, there are advantages to each of these, and in fact, a collaborative approach is what is necessary. But it's also being pointed out that there may be gaps, and it is hoped that the unmanned aerial systems can potentially help bridge at least some of these gaps. So, sort of natural question, why unmanned aerial systems? So, just a quick look at what options we generally have. So we have in situ measurements, such as buoys or ships. And these sort of give you very high temporal resolution. You can take depth measurements below the surface. For the most part, they tend to be single point measurements, which may be their limitation. Of course, you go to the other extreme, you have satellites, but they sort of give you a surface imaging. There's low temporal resolution. While it gives you good spatial resolution, I suppose you could always ask for a little bit more. And sometimes they're susceptible to cloud cover, although you have some imaging techniques that can see through that as well. Then you have weather balloons, which are quite effective in measuring the atmospheric profiles. But of course, the problem there is they're quite prone to wind drift. For the most part, they are uncontrollable. And every time these weather balloons sort of pop, there's a loss of equipment and everything that comes with them. On the other hand, you have unmanned aerial systems. So you can get controlled, say, vertical profiles. For the most part, you have a high degree of reusability. Of course, there is a chance that you could lose the equipment owing to, say, some high gusts or something else that comes up, but for the most part, you can bring it back. And it has the potential for high temporal resolution and spatial resolution at predefined altitudes that might be of potential interest. Not only that, the data obtained can feed into various facets of the center for further understanding and improving the science aspect of it. And there is also a corollary here that you could use this data to actually improve the design of the vehicles themselves and sort of feed back into this problem. Just thought I'd quickly talk to you a little bit about the roadmap and what we've been up to here in the department and what vehicles we have in store that we could potentially use for this sort of study. Everything on the top are VTOL or vertical takeoff and landing, so they can effectively stay in one spot in the air fairly efficiently. The one at the bottom is a fixed wing. So I'll just quite quickly go through the top. So on the top left is a simple electric quadrotor. But there is a reason we've sort of not been going with off-the-shelf components. For one, we feel we have the capacity to build one that actually suits our needs. And we also have, that gives us the ability to tinker, improve, and upgrade as and when we see fit. So for the most part, we've been using that as a test bed. It's a very low-cost system. And we sort of use it to test protocols when we get new imaging techniques or let's say profiling techniques, and we want to understand how basically it works, make sure we're able to get the data such that when we actually take it out, it works. So that's what we're doing. There's an upgraded version that will be flown later this year. The next one on the right is a hybrid. And what we've decided here is you take a simple quadrotor, but you stick in two wings. And the idea is it lifts up like a quadrotor, and so it can stay in one spot fairly efficiently. But then it completely tilts by 90 degrees and therefore flies as an airplane. Right? And the advantage here is you get extended range and extended endurance. You also get high ground speed, which is necessary in case you're facing headwind or, I think headwind is the biggest reason. We built this, a couple of prototypes, we're doing testing on it. The one on the right is an upgrade over, say, the one on the very left, which is we just swap the batteries and we say batteries have limited specific energy, so why not just completely switch it with IC engine and directly drive the propellers. This has been undergoing tests and we're steadily improving on it. Because owing to the higher specific energy of the fuel, you get really long endurances, and we're talking of the order of 4 to 5 hours. And for a small amount of fuel, that can actually take you to a large distance, which is sort of what we want to do: go far away from the coast, get the images or get the data and come back. At the bottom is the other end. It's a fixed wing. The advantage with the vertical takeoff and landing is you can go on a ship, sort of go somewhere deep into the ocean and then fly from there. A fixed wing requires a little bit more infrastructure, but all said and done, it definitely has its merits. We get to cover a larger range, and it has a higher endurance. We're undergoing testing here. Everything is sort of done in-house as far as the airframe, partnering, integration, and so we're hoping we'll take this out pretty soon as well. Coupled with all this, we have comprehensive set of testing facilities. I'm just showing you a few here. One is the engine testing facility, where we sort of take these IC engines, couple it with propellers, and we develop different types of variable pitch propellers that are best suited for the task at hand to maximize the mission capabilities. And on the right-hand side is a gust facility. So one of the most common things that we'll encounter on the open seas is changing winds, and that has the potential to sort of upset the the position, altitude, and attitude of the vehicle. So we want to better understand that and sort of build robust controllers and better systems to handle it. So that's what one of the facilities here is. Aside from this, there is a growing suite of research tools that are geared specifically towards aircraft design, and these are various in-house developed physics engines, everything from CFD to acoustics to conceptual design that aid vehicle design development along with mission plan. Right, so just a very quick look, and this is sort of the preliminary vehicle that we have. When we take this out, it's a basic quad rotor. It's around a 10 kg vehicle with hopefully stay in one spot for around 45 minutes. I won't go in too much into the details of all of this, but the instruments on board are an accelerometer, gyroscope, compass, parameter, GPS, different types of multispectral camera, visual, IR, etc. Of course, all of these are subject to change, and that is, I think, one of the advantages we have, that based on flight testing, we decide this works, this doesn't work, and we have the ability to swap. Don't really have much of a concluding slide, but I figured I'd just show you a snapshot from one of the tests earlier we had done. This is, of course, just a quad rotor that's there, and we have multiple cameras at different orientations, just to sort of help us see where we're going, and the inset on the bottom right, so sort of gives you an idea of the resolution and the scales that you can pick up. Those cones are placed at predefined distances so that we get to, we have some sort of a grid. This would be a little bit more challenging in the open seas. The other facet that this work feeds is it's closely coupled to algorithms for image recognition, and then sort of taking that image and pulling out the data that we need in terms of, let's say, what are the spatial scales we are saying, how does these spatial scales vary with time, and other other questions that are of interest here. So that's really all I had that I wanted to sort of talk about today, just to give you a quick overview of the activities here and how we plan to use these vehicles. And we see an advantage in using these vehicles for methodological purposes, and what is our plan and how we're going to go. So yeah, thank you very much. And yes, back to you.
Thanks a lot, Bharat. Maybe we can take a really quick question, if there is any. If not, we will have plenty of time in the rest of this week.
I'm just happy to, I'm so happy.
And on Monday
to
next
this.
week.
I wanted to compliment Bharat and his team, Devashish here. I'm just so happy to see this. So we'll talk to you later.
Sure, thank you.
Thank you, Devashish. Thanks, Bharat. Can I now request Dr. Patabi from the Indian National Center for Ocean Information Services to give this talk?
Thank you, Mani, for this opportunity. Can you hear me and see the slides?
Yes.
Okay. Good morning, good evening to all. I'm going to briefly talk on ocean observations that are being done by INCOIS. Myself, Patabi Ramaro, I'm the Group Director for Ocean Observations and Modeling and Data Assimilation at INCOIS. So before getting into the talk on observations, I would like to explain why we need the observations. Because if you see that mandate of INCOIS is to provide ocean information and advisory services to the various stakeholders, right from fishermen to disaster management officials, coastal communities, and then research and academia. So various services that are being offered by INCOIS include ecosystem services, that include potential fishing zone advisory services, coral bleaching alerts, harmful algal bloom advisory services, and coastal water quality. So we have been giving all these three services, which I have mentioned: PFZ, coral bleaching alert, and harmful, and we are getting into the coastal water quality in the next few years. So in addition to the ecosystem services, INCOIS has been providing the multi-hazard early warning services, the tsunami early warning, storm surge early warning, ocean state forecast, marine search and rescue, oil spill trajectory advisories too. So we have been providing these advisory services using a suite of models where we are meeting these operational requirements of the data, where we have designed our ocean observational network based on the operational requirements. So INCOIS has been implementing various ocean observing systems in the Indian Ocean, mainly to cater the needs of the ocean information and advisory services, and this data that comes from these ocean observing systems also gets into the ocean models and as well as the data assimilation. And these data are being used for validation of operational focus that are being provided by INCOIS, as well as understanding the oceanographic processes and air sea interaction. So most of the observational network, what I have mentioned on the right hand side, which I'll show the slide, the next slide, which provides you the spatial distribution of this observing network. So most of them are like operational observing systems that are providing data in real time, which gets into majority of the platforms. The data gets into the GTS, and then it is being used by various operational forecasting agencies across the world. So in addition to this operational observational network, we also conduct field campaigns for process-specific studies, mainly to quantify the mixing process, validating the performance of the parameterization schemes in OGCM, as well as fine-tuning these parameterization schemes. So in addition to that one, we also, as part of the International Training Center for Operational Oceanography, we also provide training to various stakeholders. So INCOIS observational network comprises of like Argo floats, drifting buoys, gliders, tsunami buoys, automatic weather stations and research vessels, wave height meter on board research ship or Visagar Kanya. We have the flux mooring, we have XBT and XCTD transects, equatorial current meter moorings, and also, as I mentioned, process-specific study observations using the state-of-the-art oceanographic equipment like UCTD, VMPs, SEMET, LADCP, ECF, and radiometers. And we are also now, in addition to the physical as well as marine meteorological observations, we are now getting into biogeochemical observations, both in the Bay of Bengal and Arabian Sea. In addition to this operational observation system in the open ocean, we have the coastal observational network, which includes the tide gauge network, where we have about 36, and we have GNSS and SMA network as part of our tsunami early warning system. In Andaman and Nicobar, we have set up 35 GNSS and SMA networks, and also we have the wave rider buoy network along the coast. We have a coastal ADCP network having 17 coastal ADCP moorings along the Indian coast. And we are going to have coastal water quality buoy network. We are going to have 4. Initially 2 we are going to deploy in this year, and another 2 in the next year. And also we are taking part of this satellite validation and calibration studies, where we are closely working with SAC and NRSC. So this picture shows the distribution of ocean observing network that is being implemented by INCOIS. As I mentioned, Argo floats, our objective is to deploy 50 per year. As of now, we have deployed about 500 floats, and out of them, about 100 plus are actively providing this data, and remaining they have completed their lifetime. And we are deploying 50 drifters per year. And we have 16 wave rider buoys, which I have mentioned. So one point which we are discussing about the coastal ocean observations. So we have a coastal observational network comprising the wave rider buoys, tide gauges by INCOIS. And also, in addition to this observational network, which I have mentioned, NIOT also has the Omni buoy network and tsunami buoys. And HF radars. We have the 5 pairs of HF radars along the Tamil Nadu coast, Andhra Pradesh coast, and then Andaman and Nicobar, and then Gujarat coast. So the data from this observing network of NIOT comes into INCOI's data center in real time, being the National Oceanographic Data Center, and it is being used for our operational services as well as it is being transmitted on GTS. We are also taking part in various international programs like the IOGOOS, INDUS, and then various JCOMOPS programs like Ships Observation Team, SOUP, and Ocean Sites. Ocean Sites is a program where Dr. Venkateshan is there on the steering committee, and I'm there on the data management committee, where we work on the standards and data transmission protocols, etc. of this Mode-V network. So in addition to these operational programs, as I mentioned, the process-specific studies, as part of the ocean mixing and monsoon program, we have deployed flux mooring, which is developed by the Woods Hole Oceanographic Institution. So mainly to observe complete annual cycle of the surface forcing, upper ocean temperature, salinity, and velocity structure, as well as the turbulent temperature fluctuations at various depths. This flux mooring is heavily instrumented with a suite of subsurface as well as the marine meteorological sensors. We have about approximately 60 sensors. It's heavily instrumented, and most of them are providing the high resolution data. This is mainly to understand this mixed layer dynamics, and as well as to refine these bulk algorithms that are being used in various models. So, and also trying to understand various processes in the Bay of Bengal. So this we have deployed in May 2019, and we have obtained data for about 15 months, where we have recovered the flux mooring in October 2020. You see here, we have got the high resolution data, continuous data for about 15 months, both from the marine meteorological pyramid sensors as well as the subsurface sensors. And one of the important observation that we have put on this observing system is direct covariance flux measurement, where we have the 20 heads data on these direct fluxes. This is the first of its kind in the Indian Ocean, where we have obtained this data. And the preliminary results shows very interesting results, that it shows that during the monsoon period, there is about 30% error in the bulk fluxes estimation compared to the direct fluxes which we got from the DCFS. So in addition to this flux mooring, we also conducted process-specific observations both in Bay of Bengal and Arabian Sea, where we have conducted 7 cruises, where we have used this vertical microstructure profilers, lower ADCP, to obtain these high-resolution observations, mainly to understand the small-scale turbulent mixing using the microstructure as well as this LADCP. So we have covered most of the all the seasons since 2017 to 2021. We are going to have one more cruise in December as well as in January. And I can say that in one of the cruises, we have already collaborated with Professor Mani to understand these internal waves of Paradeep. So probably, I hope, probably he may show the results in his presentations. So the next process-specific observation is like, as I mentioned, many of you are part of this ocean mixing and monsoon earlier. So with the successful story of this OMM in Bay of Bengal, we would like to continue this program in the Arabian Sea. As part of this initiative, our colleagues from USA, led by Professor Amit, we had several scoping workshops to come out with the science and implementation plan, mainly to improve our understanding of the physical, marine meteorological as well as biogeochemical process in the Arabian Sea, similar to that Bay of Bengal OMM initiative. So we have come out with 2 themes. One is to sustain observations and process-specific studies to understand this boundary layer process in the ocean and atmosphere in the Arabian Sea, as well as biogeochemical process. So we had partners from India. Most of the MOS institutions are part of this initiative, as well as some of these academic institutions like IIT Delhi, IIT Madras, IIT Bhubaneswar, University of Allahabad, IISCs, and also we have NIO and SAC. And our partners from US includes like UMass, University of Washington, Scripps, OSU, and NOAA, and PMEL. I'm happy to inform you that the science and implementation plan has been submitted to the Ministry of Earth Sciences, and it is being considered under the Monsoon Mission 3. So once we get the sanction order, we are going to have the implementation plan ready, and then we are going to have some field campaigns in the Arabian Sea, where we have in phased manner we are going to do that. So probably by this month end or so, we are going to get these approvals, and then we are going to initiate this observational campaign. So in addition to this, our regular operational programs as well as the process-specific studies, now Government of India has launched the Deep Ocean Mission, where we have about 6 themes, mostly talking about the development of technology for the deep sea, underwater vehicles, as well as the exploration of deep sea mining, etc., and marine biotechnology. There are about 6 themes. One of the theme is ocean climate change advisory services, where INCOIS is going to lead this particular theme, where we are going to work on the climate change aspect of the Indian Ocean. As part of this one, we are going to have observational component, where we are going to have 8 deep ocean gliders, 48 deep Argo floats, and then we are going to have the 150 wave drifters, where we are going to deploy these observational platforms over the period of 5 years. And also we are going to conduct regular scientific cruises to deploy these gliders. And we have already deployed 2 such deep ocean gliders in the Bay of Bengal during February 5th to May 20th this year, where our 2 gliders have covered 5,300 kilometers transect along 89 degrees. So our colleagues are analyzing this data, and we are going to implement this observational program in the next 4 to 5 years. So this is one important project where we are going to have strong observational component in addition to our sustained observational operational observational network, as well as the process specific studies which I have mentioned. So we have discussed about the coastal observations. You see that most of the programs in the operational network, what I have mentioned, is from the open ocean, and now our aim is to cover coastal area with more and more observational campaigns, as well as the moored platforms. So as I mentioned, we are going to set up this coastal water quality buoy network. Initially, we thought of having 6 buoys, but due to budget restrictions, that is again due to the COVID. So we are going to limit it to 4. 2 are going to be deployed during this year, and 2 during the next year we are going to deploy. So this is mainly to observe the biogeochemical parameters in addition to the physical parameters. Unfortunately, we do not have surface marine meteorological parameters. So in addition to these observations to validate and calibrate these sensors on these coastal water quality buoys, we are going to have regular campaigns, the field campaigns, where we are going to have in situ observations using the coastal vessels. So I think we are going to have the bi-monthly observations, so mainly to for the calibration validation of the sensors on board these water quality buoys. The main objective is we want to strengthen our ocean information and advisory services with new components like coastal water quality forecasting, mainly to boost the tourism and other aspects related to the coast. So this is going to be a new service which we are going to have, and then supported by this observational network along the coast. So these are all the programs which INCOIS is going to sustain, as well as continue in the next 5 years, and also include new observational programs which I have mentioned, Deep Ocean Mission, and then we have the coastal water quality buoys. So INCOIS is integral component of this Indian Ocean Observing System, which is part of Indian Ocean Global Ocean Observing System, again, which is a component of Global Ocean Observing System. So we have been participating in this initiative since beginning, that is in 2006, and we are going to continue this along with several other countries. So where we are going to complement this observational network by various countries with our observational program, where they have major societal needs and operational drivers, where we are going to observe many of these essential ocean variables. So we are going to complement this initiative as part of the regional ocean observing network. So these are the plans for the next till 2026. So we're going to sustain all these observational network which I have mentioned, and then new components now, so that that also we are going to continue. So the main focus will be like the observing the coastal ocean is going to be our target. We are limited, as Dr. Venkatesan has mentioned, we have some limitations in taking the observations in the exclusive economic zone. Particularly, we should not transmit the data in real time. But recently, in the last week, we got some approvals to operate some of this ocean observing equipment with some riders. I think we are going to come up with a solution so that we can get more and more coastal observations in the coming years. So with this, I conclude my presentation, and thank you all.
Thank you, Dr. Patabi, for that informative talk. We will look forward to continued interactions with INCOIS. So in the interest of time, I will just move to the next talk, and we will have time for discussions surely on Monday. Thank you very much.
Thank you.
I now request Dr. Venkatesan from National Institute of Ocean Technology to give his talk. Dr. Venkatesan?
Yeah, I am uplinking it. Just wait a minute.
Yeah, sure.
Is it seen now?
Yes.
I've shared it. Yeah. Good morning, good evening to everyone. And I really wish and the efforts taken by Dr. Mani in bringing out such a wonderful proposal. And he has been interacting with me, and I could see the team, what he has developed. And I will add the contribution what NAOT can do from the Mood Boy program for his effort. And we are all part of a larger program, and the Indo-US program in Bay of Bengal, which Dr. Debashis and Dr. Amit and Eric and many of us who are associated, who are here, are associated in that. So this is a simple picture to show you how this is the 25th year of this Mood Boy program. In fact, we have a linkage to IIT. The whole program started in IIT Madras, and the initiative has grown so big that so much data sets have been collected. And this particular slide speaks volume about quantum of data, what we have collected. And Dr. Mani has told me to speak a little bit on technology component. So slightly, I will show that. This is a larger network comprising of both Omni and Rama network. The Rama network is under the Indo-US collaboration by NOAA PMEL, which earlier INCOIS was dealing in 2017. It was transferred to us. So this talks about how much amount of data being collected by us, and that is available for the scientific community to understand about it. These observations having subsurface measurement for the past 10 years have really shown a great interest and made us to understand more about it. And this contribution of this Mood Boy speaks volume, particularly when you look at the publications, what this group has come out last almost about 7 years. We have been having about 18 to 22 publications. In addition to that, a book was published by Springer. And also all the efforts of the Indo-US collaboration, these Omni network played a major role. Now, keeping this in mind, during the recent the renovation or renewal of the contract between India and US, our secretary and chief secretary of NOAA, we have signed an agreement, and this Mood network will be further maintained for next 10 more years. And there is a commitment from the government of India to provide the ship time. And we can see that there's a common portal was launched, which the former secretary, Dr. Rajivan, had announced it. And we continued, and thanks to Dr. Patabi, Dr. Srinivas, INCOIS, NAOT, and Rama Port all joined together, and this portal is available, where about 9 OmniBoy and 25 more Rama Boy network data sets are freely available for anyone, for any student to use. Only here is that the Rama network is a taut mooring, and Omni network is slack mooring. And also you can see we have clearly given what are the different type of data sets available. And there are more amount of data you can see from the Omni network, thanks to Dr. Debashis, and he was part of the earlier team way back in 2009. And that has made us to add additional sensors. And today we have, with that experience, we are able to say that the quality of data sets what we are providing is good. We have also done many intercomparison exercise. In particular, I would like to highlight here, nowhere in the world we have a large amount of wave data from 3 in Arabian Sea, 3 in Bay of Bengal for a continuous period of more than about 8 years we have. So that is the main contribution. All are available. Anybody wishes to have more data, more detail, either they can contact me or Dr. Patabi. Now, we are talking about observation, why do we need? And so when you talk about society, okay, science component is one, it should reach the society. Here is a classic case. We had a peculiar situation, 2 consecutive years, we had a similar type of cyclone, and one followed by other in Bay of Bengal and Arabian Sea. In all these cases, these mood buoy were functional. And the interesting part is these are all during the COVID pandemic, where most of us were staying at home, and a few of my colleagues had to sail out and make these things functional. So both Amphan, in the case of Amphan cyclone, more than 10 lakh people are evacuated, which was appreciated by WMO, and they wrote a letter to our Director General of Meteorology. In addition to that, we had a rapid mode data transmission, which worked very well. And we know for the forecast, there are 6 parameters required. Out of the 3 are from ocean. In this case, 20th of May 2020 was the landfall in Calcutta. However, from 12th itself, we could have the track of this mode, and this mode buoy were providing continuous data sets to us. So Dr. Mani also wanted me to show about this state-of-art data reception facility, which was functional even during pandemic, and is really providing very good information. Now, this has not only the raw data as well as metadata also is available. We are part of a global exercise where OceanOps, earlier it was called JCOPS, we are sharing the metadata with them. And also through GTS, these data sets are through INCOIS to IMD, it is being shared. We have also formulated a methodology by which what is being given by IMD is verified by us. There is a closed loop system, it comes back to NIOT. We have a very robust data reception facility, and also the best practice developed. This is what I would say that our pride, India's pride, to have such a good facility for us, and all the information data sets what has been collected, either it is in INCOIS or in NIOT. We have a very seamless system by which any data collected by us is transmitted to INCOIS. Absolutely, there is a very good working mechanism between these 2 teams in INCOIS and NIOT. That's the best part of the whole exercise. Now, Dr. Mani wanted me to show about technology transfer. We had in this process, it is the institute being a technology institute. Okay, we have been collecting data. We have also taken exercise to develop various tools like robo-coastal observer, similar to what has been shown, and robo-boat, which could be used by 4G and could be controlled from the office to collect. And that will collect the data from the estuarine to river to the estuarine to the coast to the deep ocean. It can sail through that. And of course, we have Moon Buoy, both MetOcean as well as the Omni network, which has got a subsurface measurement. And the Tsunami Buoy ours is called Sagar Bhumi. I'm also chairman of the International Tsunami Partnership. There are 13 countries having the Tsunami Buoys. We are one among the, other than the US, to have our own system. We are sharing the data with UNESCO IOC that is available in NEBC. So that is the biggest strength for us. So recently, L&T has taken this transfer of technology from 6 of the technology what we have got it, and we have also filed a patent, and 2 of them are awarded. There are 4 more units which we have started filing their patent. That's the reason technology transfer we have delayed. Basically, we are talking about basic observation system, which I told you, which can be incorporated on board the boat. There is also a deep ocean autonomous video recording system, which we developed a low-cost part of it. And we have ARG, that is for the atmospheric technology we have developed, like ARG, indigenous rain gauge, which we have installed. Presently, it is part of the national loop with IMD Pune, one in NAOT, one in NAOT Nellore. You may be seeing soon these data sets also part of it when the forecast is happening. We are also developing a universal data acquisition system, which could be used for any system, whether it could be terrestrial, agriculture, or ocean. This is only unit. So these things are happening, and thanks to the technique and we have developed, and the expertise have come mainly because of interaction with the international institutions and community who are with us and collaborated. Due to paucity of time, I'm not talking much in detail. I would like to say that last 25 years, we have grown from a smaller 14 parameters. Today, we are having about 125 parameters being transmitted. We are part of an ocean science reference station where one in Bay of Bengal and one in Arabian Sea, we are sharing the data. And we are also having exercise. There are 3 decade program like Oasis, that is for air-sea interaction, deep ocean observation DOOS, then ocean best practice. And all the 3, we are part of the executive committee where we interact with them. Another important thing, collaboration with Dr. Amit. Currently, I've come on a Fulbright fellowship. I'm in UMass Dartmouth. He is also interacting with my colleague, and one of the important work is on Stokes drift. Basically, we know that the wave component is not much studied. Dr. Kalyani, a mathematician, she is doing good work, and that has been initiated. And on the LWR, long wave correction, radiation correction, which Dr. Josiah is interacting, and the paper is almost ready, it is communicated. And another interesting phenomenon we got from the ocean sites location is the temperature and salinity data collected close to the seabed, up to maybe 1,000, 2,000, and 3,000 meter water depth, had a signature of the monsoon, which Dr. Martin is working, and Amit and Bobble, they are interacting with us. Soon we'll be publishing that unique results. And Amphan cyclone has really helped us to understand more about it. There's a larger interest in the science component, which Amit is coordinating with Sundar, and soon there is a JOT paper which will be published one more on the climate studies. So with this, I can say that the team has grown in a bigger level. There's not only the technology component, there's a science component do exist, and that will be continued in the days to come. This is what, as the science part of it, we have contributed. We will be developing, because in the larger exercise, I'm also talking in the global level, large amount of fishing communities are there. We can collect the non-strategic data like air pressure, temperature, and SSC. And for that, we have developed a module, and we have installed in a fishing boat. Today or tomorrow, it will be sailing out. We call it as the FE boss. Once that is done, this we want to show. This again, I told you, World Meteorological Organization, there we want to show that. So because Dr. Mani has just sent a mail to me about after my intervention when Dr. Zaguta said, I thought I'll just brief you. This is what is a WMO reform, where after 70 years, there is Earth system approach is coming through. I am a vice chair in a study group on ocean observation infrastructure systems. We regularly meet and discuss. Out of 8 committees that has been merged into one, Infrastructure Commission and Services Commission. So now there is a larger role to play by the ocean community. There's going to be a newsletter released next month where exclusively on the ocean part of it, we have discussed about it. There is a regional association which WMO is well structured, and there also we are going to have not only meteorology, hydrology, and oceanographic component will exist. So the science is reaching to the policy level, and it will be much more useful in the future on the forecasting, particularly on the climate forecast part of it. UNESCO, I will say, yes, is always aggregating what has been asked earlier also. When we can't manage, because what we do not measure. So the observation is a key over there. So we need to emphasize on systematic observation. We are also talking about technology development. There's environmentally supported technologies required, where GOOS and Marine Technology Society, we have formed a team. We are also interacting with the industry. So like what has been presented earlier by Dr. Balaji is we call it as an uncrewed vehicle. For that also we have a WMO identification number, WIGOS ID, but that has been developed in the larger level. I was also invited last year to speak in the hurricane high-level committee in the NOAA, where I was happened to see the similar type of uncrewed vehicle being deployed during the hurricane. Similar such activity would be interesting. I was also interacting with the DGIMD, and Dr. Mani had presented to them on the drone what they have developed. I could show them there is one drone which can go very high altitude, which IIT Madras can do. IMD is ready to work along with them. So there are many more direct application-oriented results would come by this effort which he has initiated from this program of GFL. I'm sure that this will exceed. This is a regional level, how GRA and Goose Regional Alliances is distributed in 13 regions. 2 are individual country-oriented, Australia and US. 6 of them are like UNESCO IOC Commission. 1 in Goose Africa is developing. There is 1 in Euro Goose has got complete value chain from observation to the product and reaching to the society, which is supported by an independent organization. So this is what we are trying to see, how this GRA can be merged with the WMORA, which if we succeed that, definitely whatever research we are doing, there's a more amount of research community getting involved in that. Even research activity will be having a WMOID so that the metadata what has been collected will be properly documented. These are all the efforts. We want to start with research vessels where the research vessel can share the data after the completion of the cruise. At least non-strategic data could be shared with them. So days to come with the global exercise, what is being done, there'll be more integrated approach to understand about the ocean along with the system as a whole. Thank you very much. Thanks to Dr. Mani for making me to brief this effort. By your mail, I could do that. Thank you.
Thank you, Dr. Venkatesan. That was very informative, and thanks for your words of support. We will look forward to continuing our interactions with NIOT. Thank you. So in the interest of time, we will move to the next talk by Amit Tandon from the University of Massachusetts at Dartmouth.
Thank you, Mani. Can you hear me?
Yes, Amit.
All right. And just wanted to make sure you can see my screen.
Yes.
All right. I'm going to change the direction a little bit and bring you back to the dynamics. As Mani said in the beginning, one of the things that the center wants to do is to also work on process studies, perhaps near the coast, but also in the open ocean. So I'd like to talk to you about sub-mesoscale processes in the ocean with an example from the Bay of Bengal, based on some experimental work that we did together with India. So there are a number of collaborators that I've been working with on sub-mesoscale process over the years. And this work has been supported by the Office of Naval Research and some of it by the National Science Foundation. One of the questions that McWilliams asked in his review papers was, how do the energy and properties get flux downscale? How does the energy in the ocean get to dissipative scales? We know from microstructure observations that there is a lot of dissipation, particularly in the surface ocean and near the boundaries, much less in the interior of the ocean. We also know from the ocean dynamics ideas that at the larger scales, the energy actually goes to the larger scales. It's injected at the Rossby radius of deformation, but it goes to the larger scales. So at mesoscales, when we have much, Rossby numbers much less than 1 and Richardson numbers much greater than 1, stratified low Rossby number flows, the dynamics are mostly hydrostatic, they are non-dissipative, and the energy flows to the larger scales. At the smaller scales, where the Rossby numbers are much greater than 1, Richardson number is much less than 1, the dynamics can be non-hydrostatic. And what connects the mesoscales to the smaller scales are the ocean processes at sub-mesoscales, which are particularly active near the boundaries. So these could be surface boundary layers, or near the bottom boundary layers as well, and particularly near fronts. So I'm showing you in the background a slide from the Arabian Sea. Oops, my My slides have suddenly become frozen. Let me see if I can fix this. Okay, maybe you can see it now. So here is a green blanket on the Arabian Sea that you see from a New York Times article, but essentially what it's showing you are larger scale eddies, mesoscale eddies, which are stirring the chlorophyll that we can see from the satellites. But what you also see are many smaller scales embedded in between. The mesoscale eddies are stirring these filaments into ever thinner fronts and filaments, which have important implications. This dynamics has important implications for subduction of heat, for vertical exchange of nutrients, for carbon cycle and biological pump. So how do these processes arise? From some basic dynamics, we know that a very important variable in the ocean is what's called the potential vorticity. And in the absence of friction and in the absence of diabatic processes, what is conserved is the potential vorticity. At the largest scale, this potential vorticity consists of just Earth's planetary vorticity, and at the basin scale, what is conserved is Fn squared, so we're near zero slope, has a very low Rossby number. As one goes to smaller than these 10,000 kilometer basin-wide scales, one gets to ocean mesoscale, which is where the quasi-geostrophic dynamics is active. And the eddies basically are arising from the baroclinic instability of the thermocline. So we're talking about vertical scales of order kilometer, horizontal scales of hundreds of kilometers or order 200 kilometer in the Bay of Bengal. And the potential vorticity now is primarily governed by the vorticity that's due to the Earth's rotation, as well as the vorticity inherent in these mesoscale eddies. At this scale, the density surfaces have small slopes. Rossby numbers are still very small. And vorticity dominant regions, we can separate them out from strain dominant regions, as is often done for remotely sensed data set. Once we start looking at slightly smaller scales, and I mentioned that this is where ocean fronts become important. You can see that if the density surface is outcropping, then you don't have small slopes of the isopycnals anymore. In presence of density gradients, these density gradients tend to lower the potential vorticity. And in general, what that means is that the flow can now go unstable to new kinds of instabilities. So that leads to things like mixed layer instability and symmetric instability. The reason why I wanted to talk to you about is because these instabilities can also play a role in setting the stratification of the ocean, in particular, including that in the Indian Ocean. So the submesoscales are intimately linked with processes that modify the potential vorticity, such as the surface forcing by the wind stress, the frontogenesis because of the mesoscale eddy stirring, and that leads to different classes of instabilities. I just wanted to show you one example of these instabilities that arise in the Bay of Bengal, and this was done in collaboration with India, with US-India collaboration. This work has been published in the Journal of Physical Oceanography, led by Sanjeev Ramachandran, myself, and many other co-authors. So we were on Roger Revelle in November 2013, just outside India's EEZ, and there were two. We are in the zone between two mesoscale eddies, which are being shown by the sea surface height plot on the outside, and in the inset are ship-based transects that are marked sort of A, B, C, D, etc. And what's being shown here is that there's a surface front with lighter water to the north and heavier water to the south. Much of this is coming from the eddies are inducing a mesoscale strain, which is order 0.15 F. We did a survey of this front going from east to west in the direction shown with fairly high resolution, and the duration, each transect was about 4 to 6 hours. So you can think of each transect as sort of an independent snapshot of what is happening in the ocean. Well, what is happening in the ocean is that you see the black lines as the isopycnals, and in each case, we've marked the position of the front by a vertical arrow. as time goes on, you see a large volume of warm water which gets subducted, which is being subducted. And you can see that in particular in transit B here, that a lot of the gradients in the top 40 meters are actually coming from the salinity gradients, whereas when you go further down, it's the temperature gradients that are more important. So the salinity, so there are strong salinity fronts near the surface, and these are there are also some pycnostats subsurface. The reason why I wanted to bring these to your attention was that you heard from Debasis this morning how subsurface warm water in the Bay of Bengal can lead to cyclones that retain their intensity, or they reach their potential intensity because they can mine into the subsurface warm layers. So one of the things that this process study showed us was that in presence of mesoscale frontogenesis, the eddies are, pinching these fronts and filaments, and given the right orientation of winds and cooling as well, this leads to low PV water, which then can be warm and can get subducted and form these large pools of warm water that are then available to severe events later. So a summary of my talk is that the submesoscale processes in Indian Ocean arise frequently. Fronts in the Northern Bay are sharp, they're shallow, they're stratified. Observations at a salinity front that we did in 2013 and one particular process study showed that force with downfront winds and moderate mesoscale frontogenesis, there's a huge range of submesoscale processes that arise. They lead to lowering the potential vorticity, and we showed that the conditions for various instabilities are satisfied. Below the top 10 meters, the isopycnal thickness and the vorticity vary together. It leads to pycnostats, which are order 10-kilometer lateral scales. Similar structures have been seen in the Arctic, and they've led to very interesting work by Jen McKinnon and her colleagues. We did complementary numerical studies for the Indian Ocean, which showed that low PV water subduction, like the ones that we saw in these observational studies, could create significant temperature inversions in the bay. So I wanted to show you just as an example of a case where the observations and numerics work together to understand one of the key processes happening in the Bay of Bengal leading to subduction of warm waters. There are many very interesting processes that occur in the Arabian Sea, so I'll just leave you with these two tantalizing images from the Arabian Sea, where we see many submesoscale processes happening, not just in the coastal upwelling region off of Gujarat, but also leading to some very interesting dynamics in the open ocean, the Arabian Sea. So more to come. Thank you.
Thank you, Amit. So if you don't mind, we can keep the discussions for later in the week or Monday.
Sure.
And thanks a lot, Amit. Can I now invite Jonathan, Simon, and Emily from the Oregon State University?
Hi, can you see my screen?
Yeah.
This is Simon DeCirca at Oregon State University. I see Mani nodding. Thank you, Mani, and all of the previous speakers and speakers to come for joining us today. I'm going to be talking about, like many of us, talking about air-sea interactions in the Indian Ocean from the perspective of some of the surface following craft and measurement platforms that we've been developing and using at Oregon State University. And this is a collaboration, and you'll hear Jonathan Nash chime in the next couple slides. And we also have Ken Hughes and Emily Schroyer and Jim Mohm have been working here on these platforms and observations as well. All right, oh, that's a very big, busy slide. So I really liked the introduction by Craig, for example, so I'm gonna ask, on what scales does the atmosphere or atmospheric intraseasonal oscillations respond to the Indian Ocean warming and the sea surface temperature. And I'm going to just provide two examples in this talk, although there are many others. And one is the diurnal warming of the sea surface temperature, which is forced by the solar cycle, sometimes is greater than 1°C. Maybe estimates vary, but maybe 2% of the time. And if that's true, then it would account for a vast and changeable part of the tropical oceans, about 3 times the area of India. And then the second example is of the atmospheric response is that the atmospheric response, that was the ocean responding to the solar cycle. The atmospheric response is that there are diurnal pulses of turbulence that generate clouds. And this has been known over land for a long time, but I'll show you some new observations of this occurring over the ocean. And then on a completely different basin scale, the scale of the MJO, is that when sea surface temperatures warm up on intraseasonal time scales, then they induce, we can model how they induce moist-static energy convergences. And hang on, I'm pressing next, but I don't know. It's going to take a little while, I guess, to go to the next. There we go. Hopefully it doesn't go forward again. Jonathan, are you there?
I am. Hey, I just wanted to thank Mani and the entire group in India for involving OSU in this project, because I think it's really a great time for us to be collaborating. And I guess I'm not going to show any science really, but I did want to say that we have a bunch of, I think, some parallel technologies and interests that that we could work on together. We are also interested in a lot of autonomous types of instrumentation. And here I'm just showing a couple examples. One of them is Jim Mohm's surf otter, which was designed to measure the upper 2 meters of the water column. And Simon's going to show us a few more data from that. And then we've been building autonomous kayaks and with turbulence and other instruments on them. And more recently, we've sort of upgraded to some autonomous boats that are powered by outboard motors and Garmin autopilots and whatever. And we're happy to share what we've learned on those. All these sensors, you can go to the next slide too, Simon. These all tow thermistor chains, and so we, as we move along through the water column, profiling around, driving around, we're towing sensors that are measuring temperature at very high horizontal resolution. Simon, can you move forward?
Yeah,
oh, there we go. Perfect.
Wow.
That's great. And this is just one example that I wanted to show. And this actually comes from the Gulf of Mexico from earlier this summer, but we have a lot of similar types of data from the Bay of Bengal as well. And what we love to do is measure the temperature structure on very, very small horizontal scales over varying distances, but to try to understand the role of the near surface ocean and how it interacts with the atmosphere. And this is just one example where you see a lot of variability on 1 to 5 meter vertical scales, and then 1 to 10 to 20 meter horizontal scales. You see a beautiful interleaving pattern here and very sharp fronts and a variety of things. So I'm going to turn it over to Simon, and he'll continue the rest of the talk. But we're super happy to be part of this this project that you guys have started.
So here's another example from that surf otter that Mohm and Schroyer had been developing. And this is an example from a paper by Ken Hughes from 2020 of the diurnal warming. This is one day, and the red colors are warm temperature anomalies in the upper 2 meters measured by the surf otter. And so this is the daily warming in this case. So there's several really nice examples, and this is one where it warmed by, I think, about 2 degrees. And here's another. We have some concurrent observations, but I'm not presenting concurrent observations. Here is an example of observations of the sea surface temperature and the 5 meter temperature from a ship in the lower panel. And in the top panel is the solar radiation. On these days, the temperature warmed by an average of 1.5 degrees each day. And I'm going to show observations from a Doppler LiDAR, which looks like this instrument in the back van over here, near my words. And I've added a green laser beam. It actually has a green laser beam, but you can't see it unless I added it. I enhanced it by PowerPoint there. This is called the NOAA. This is a NOAA instrument called the NOAA High Resolution Doppler LiDAR. And these are observations from the equatorial Indian Ocean from Dynamo. And when we analyze all of the turbulence data, we can compute dissipations, and these are dissipations scaled by buoyancy flux. And the scaling by buoyancy flux agrees with a lot of geophysical flows and mixed layers in oceans, lakes, and over land, in Minnesota wheat fields, for example. So that was reassuring. And then we can use this to build an idealized profile, and using the actual mixed layer depth of this is the buoyancy flux in the top panel, and we scale up this profile by the buoyancy flux at each individual time in the lower panel. So you can see the mixed layer is pulsing due to the increased buoyancy flux due to the warmed sea surface temperature. And also what happens at that time, when we have these deeper mixed layers, the mixed layers are reaching the lifting condensation level and generating clouds in the afternoon. The lifting condensation level is orange, and incidents of clouds are indicated by the gray dots. And you can really see in these first 3 days that these pulses of deeper mixed layers over warmer sea surface temperature in the afternoon are generating clouds. Okay, I now have another example on very different time scale. Yes, very different spatial and time scale. And this is the intraseasonal time scale. Turns out that these times where the wind is very calm in the intraseasonal time scale, the ocean warms up. I showed you examples when it warms up each day by a lot, but if we average over all of the times that it warms up a lot and a little and night and day, the temperature warming is about 1/2 degree, not 1.5 degrees over an intraseasonal cycle. And so here's, this is the warmest phase in the central Indian Ocean in phase 8 here, the second panel from the top. And this is each panel here with time moving downward is the sea surface temperature anomaly composited from satellites by the Madden-Julian oscillation intraseasonal phase. So each slide maybe represents about a 5-day average of sea surface temperature. It's not quite that simple, but just to give you an idea of time scale. And we can use this and just model the hydrostatic gradient of pressure induced by warming the air up over this warmer sea surface temperature. Sea surface temperature is actually really easy to observe from satellites. Well, yeah, it's kind of easy to observe. Air temperature near the sea surface temperature is really hard to observe. An order of magnitude harder than sea surface temperature anyway. And so we can, and then from that hydrostatic pressure gradient, we can compute, or geopotential gradient written here, we can compute the divergence. And that divergence pushes together warm, high moist static energy from lower in the boundary layer with warm and moist air near, it pushes it together and it increases the column moist static energy indicated by the green funk here, and that drives deep convection. So I'll show you the result of that model. So now the colors are the moist static energy convergence. And the convergence actually occurs 10 to 20 days ahead of the convection, the rain in the Indian Ocean. And it accounts for about 7 watts per meter squared moist static energy convergence over a large region. If you can see, it's the region of this black box I've drawn here in each panel. And in some particular pixels, it could be accounting for 40 watt per meter squared convergence. But these things probably should be averaged. They are second derivatives in space after all. So I've shown two examples where fine scale and diurnally I've shown an example where fine scale and diurnally forced turbulence in the ocean affects the turbulence in the atmosphere. And several of our speakers like Craig and Debasis have shown how persistent sea surface temperature anomalies bridge the fine scale ocean processes and dynamics to basin scale dynamics. And I've shown a particular example here, another particular example where the atmosphere responds. Diurnal pulses of turbulence generate clouds very locally, and intraseasonal SST anomalies that develop because of the weather inducing certain processes in the upper ocean contribute to basin scale moist static energy anomalies. Thanks for your attention.
Thank you, Simon and Jonathan, for that very interesting talk on air-sea interactions and little bit of detail on the technology and autonomous vehicles. I'm sure we'll have plenty of opportunity to discuss in the rest of this week and Monday next week. Thank you very much. Can I now invite Tom Farrar and Amala Mahadevan from the Ujjwal Oceanographic Institute?
Okay, I'll go first. Let me share my presentation. So Amala and I are up next. Amala and I work closely together on many things, but we decided to split our talk into two to introduce ourselves. So I'll mostly be talking about some platforms for measurements of air-sea interaction. The ocean supplies heat and moisture to the atmosphere, and it's really the sea surface temperature field that the atmosphere can feel. And this is the primary way that the ocean affects humans, at least in terms of the weather and climate, is by these air-sea fluxes. And it's especially interesting in the Northern Indian Ocean because of the special role of the unique and strong salinity stratification there. So oceanographic surface moorings are one way to measure air-sea fluxes and the upper ocean evolution. And my group has been working with people from NIOT and INCOIS and the Indian Institute of Sciences to do this for several years now, about the last decade. And that's a great way to get a year-long time series of data that can be used to understand air-sea interaction and the upper ocean response. Another technique that I find interesting and that we've been pursuing for the last several years is what we call a drogued buoy air-sea interaction system, or Devasis buoy. These are buoys with drogues near 200 meters. And what's nice about this is that they're cheaper than a surface mooring, and we can deploy a few of them for a short time and collect high quality surface measurements. We did that on a cruise in the Bay of Bengal in 2019 and deployed 3 of those buoys that drifted around the perimeter of this eddy. And to a large extent, the 3 records look more or less the same, which you would expect since they're about 20 kilometers apart during their drift. There was an event there was an event with strong atmospheric frontal passage and strong spatial variability between the buoys. And I just thought I would show a zoomed in view of that, where we saw big differences between the 3 buoys in terms of the surface heat fluxes. And in that event, the air temperature dropped by 3 degrees Celsius and the wind speed increased by 15 meters per second over a few minutes. And we had 10 centimeters of accumulated precipitation. So these drifting buoys are a great platform, especially coupled with the Scripps wire walker beneath the surface, which is a contribution of Drew Lucas to this. We get a really good view of what's going on with temperature and salinity and velocity beneath the surface in response to these events. So the final point I want to make is that I'm really excited about the potential for autonomous surface vehicles for measuring air sea fluxes. This is a wire walk or a wave glider that's a wave propelled autonomous surface vehicle. And with people at Scripps, my team has been working to instrument these for air sea fluxes. And this buoy is carrying, or this wave glider is carrying essentially the same instrumentation that our buoys carry. And, you know, we've been doing this for a few years, and I'm really encouraged by the quality of the data, especially the radiation data. The shortwave and infrared radiation data seems to be a really high quality, and it's a good platform for those kinds of measurements. So that was really all I wanted to say, and now I will hand over to Amla. Amla, are you there and ready to present?
Yes, I'm there. Sorry, I'm not able to get my screen to share for some reason. Yikes. All right. All right. Maybe I can, I have no idea why it doesn't share, but I'll, give me a second. Is there someone after me who wants to go?
Yeah, there is Neeraj Agrawal from Space Application Center. Do you want us to go ahead with him and then you'll come back?
Yeah.
Cool. Okay. Thanks, Amala. Neeraj?
Thank you.
Yeah. Could you please go ahead with your presentation?
Yeah.
Then we'll
So
come
I'll
back.
share my screen.
Yeah, please.
So is my screen visible?
Yes, Neeraj.
So hello, everyone. First of all, I would like to thank Mani for giving me this opportunity.
Neeraj, you could go into
glimpses.
slideshow mode. It may be better.
I'm already in the slideshow mode.
Okay, then please go ahead.
Okay. So I would like to thank Mani for giving me this opportunity to present some of the glimpses of what we do at the Space Application Center under the theme of satellite oceanography. I'm
Yeah, Neeraj, we're not able to hear you. Anubhav, are you able to hear me?
Mani,
I was
I
able to hear
also, I don't hear Neeraj either.
Okay. Let me try and give him a call.
Anubhav, can you make Amala co-host? Okay, I see that's been done. Amala, do you want to test if it works?
Yeah, let me try.
Just to see if it's any better while we're waiting for Neeraj.
No, but I've mailed my slides to Mani.
Okay.
Sorry, I just upgraded to Big Sur, so I know that's something got messed up.
So Neeraj said he had an internet issue and is trying to rejoin. Amala, if you are ready, you could go ahead.
Can you show my slides, please?
Yeah,
I
please.
just emailed them to you.
Okay.
No, could you show them if you don't mind?
Yes, yes. Give me a second.
Okay, maybe I can, thank you so much, yeah. So I wanted to talk about this problem that a student of mine, Jinghe, and I are working on, and it is motivated by the fact that when we look at sea surface temperature in the Northern Indian Ocean, what you'll find that in April and May, both oceans, Arabian Sea and Bay of Bengal, are very, very warm. And when the monsoon starts, when the summer monsoon starts, what happens is that the Arabian Sea really cools off the sea surface temperature. And this affects the way in which the Bay of Bengal continues to have these monsoon intraseasonal oscillations, and the development of all these storms that you see over the Bay of Bengal continues throughout the monsoon season. So next, Mani. So the question is, why is that? Why are these two different oceans have very different sea surface temperature? So we looked at the phenomenon that we are looking at is coastal upwelling. So when the southwest monsoon starts, you can see that the winds blow from the southwest, and you get coastal upwelling both on the coast of in the Arabian Sea on the western side, and you should also be seeing this on the Bay of Bengal. But if you look at sea surface temperature, the Arabian Sea is about 4 to 5 degrees cooler than the Bay of Bengal. So what's happening there? Why are we not seeing that upwelling signal in the Bay of Bengal, which should have cooled it off? So the upwelling strength, as you know, depends on tau over rho f, where tau is the alongshore wind stress. And so we started by looking at that wind stress. And in purple or magenta is the Bay of Bengal. Wind stress is the dashed line, and the bold line is sea surface temperature. And in blue, you see the Arabian Sea. So what happens in the Arabian Sea is that as the wind stress develops during the southwest monsoon, this is the southwesterly wind stress, you see that peak in the dashed line in blue, the SST drops because you have this coastal upwelling. And so the SST is very warm in April, May in the Arabian Sea, but really drops off during the southwest monsoon. Whereas in the Bay of Bengal, when you look at the seasonal cycle, it drops a little bit, but it stays warm. So next. So what this slide tells, Mani next, please. So what that tells you is that the upwelling strength depends on the wind stress. But what matters for sea surface temperature is not just the strength of upwelling. We also want to know the depth from which that water is drawn up to the surface. So I wanted to consider two different scenarios. One is what the Arabian Sea kind of scenario to the left, you have weak density stratification. And when the winds blow along the coast, you'll have an offshore Ekman transport, and that will draw water up near the coast. And that has a deeper source depth than in a situation in which you have very strong density stratification. So with strong density stratification, the same wind blowing along shore, Ekman transport, the strength of the upwelling is the same. So the volume transport is same because it depends on tau only divided by rho f, but the depth from which you draw water will be much shallower. Next, so we wanted to demonstrate this, and we used a model. So we use this process study ocean model. We're blowing winds along the coast. This is a 3D image, and you get this upwelling at the coast, but in a 3D model, that upwelling front becomes unstable and it generates eddies, and those eddies tend to try to slump that front back. So now we have a kind of a quasi-equilibrated strait. The wind is blowing, it's creating this upwelling front, and the eddies are trying to restore the stratification. Next. So what we did is we tried to come up with the scaling. We said, what is the depth, that D, from which we get ds, from which we are drawing up water? And what we did is we equated these two these two overturning stream functions. One is the wind, which is drawing water up at the coast, so that's the upwelling strength. And the other is the eddy-driven overturning, which is trying to restore the stratification. So once the eddies develop and this front is unstable, we can equate these two and come up with what the source depth is, that's ds, and that's our scaling for the source depth. It depends not only on the wind stress, but it depends on n, the stratification. So shallower, stronger stratification is shallower source depth. Next. So we're going to test this in a model. And what we do is we run our model simulations by varying the wind stress, and we do 9 simulations, different wind stress, and by varying the stratification. And in these figures, in the lower panels, you're seeing these little snapshots of the source depth. What you can see is that the highest wind stress and the weakest stratification is when you get the deepest source depth. Next. And so we can plot all these on a plot, and we can see that our scaling is not bad. We get a source depth which varies with the stratification, not just on the wind stress. Next. And what we can conclude about the Bay of Bengal and Arabian Sea is that they do have different wind stresses. So the Arabian Sea has a much stronger coastal wind stress, a longshore wind stress, as you can see in this table. But the Arabian Sea also has a weaker stratification. And so the source depth of water in the Arabian Sea, this is just from our scaling, is much deeper. It's about 200 meters, whereas in the Bay of Bengal, that source depth is much shallower. And so if you look at two temperature profiles for the Arabian Sea and Bay of Bengal to the right, and the source depth is shown in the dashed line, you'll see that the Bay of Bengal cools, but very little. That then the difference in temperature between the surface and the source depth is very little. Whereas if you look at the Arabian Sea profile in blue, the difference between the surface temperature and that source depth is much more. So that's why you see a much greater cooling. So it's very related to what many of the people were talking today. But thank you. Stop there.
Thank you very much, Tom and Amala. I'm sure we'll have opportunity to discuss on Monday. Neeraj had an internet issue. He is now back online. Neeraj, could you please present now?
Yeah. Am I audible now?
Yes, Neeraj.
And the screen is visible?
Yes.
Okay, cool. So I'll quickly sum up what I was speaking. So our mandate basically at the Space Application Center is basically to build applications using satellite observations for societal benefit, value-added information and algorithm development and implementation of data assimilation techniques. And then the very important component or very important activity that we take up is basically to define the future space-based sensors by performing observing system simulation experiments. And then we also do satellite-based and model-based process studies. So on my right, I show a very high spatio-temporal resolution image from the INSAT 3D satellite, which gives at every 30-minute interval the various geophysical parameters. So this is one instance of the rain rate during the Amphion cyclone. So one can see the capability of this satellite that it can capture the highest temporal and spatial scales of variability during such events. So we have currently Saral Altica, then SCATSAT, RISAT, INSAT 3D, 3DR generation of satellites. And in future, we will be having the OceanSat 3, which is renamed as US6, and then the SCAT mission will continue. Then we have the ISRO-NASA joint synthetic aperture radar named NISAR, and then also coming up in future will be the INSAT next generation of satellites. So some of the value-added products that we are developing routinely are available on www.mosdec.gov.in. So one can have a look at that. These are available for download. For example, the eddy parameters such as the shape, size, and the amplitude of the eddies, whether it is cyclonic, anticyclonic, all these information from altimeter are derived and kept at Mosdec website. Then we also provide the sea surface current estimates from altimeter and scatterometer. And then we use we use basically the quasi-geostrophic approach to project the satellite derived SST, sea surface salinity, and sea surface height into the subsurface density and velocity anomaly fields. So these fields are also available on MOSDAQ. Then we also have geophysical coastal products derived from Saral Altica mission, which are available, and then high resolution analyzed wind fields from the scatterometer. So all these products are available in near real time on MOSDAQ website. The application front, basically, we are mainly working on the development of data assimilation techniques to maximize the usage of the satellite observations for improving the ocean state estimates. So we have developed data assimilation techniques for assimilating sea surface height from the altimeters, then sea surface temperature, sea surface salinity, and chlorophyll. And these are getting assimilated into high resolution numerical models of circulation and wave, mainly to generate reanalysis and also to perform observing system simulation experiments, wherein we do sensitivity experiments by constraining the models from observations available from various sensors and a combination of sensors. Then we are also working with advanced data assimilation techniques like particle filter image assimilation. We are also working with high resolution biogeochemistry modeling, wherein we have developed techniques for assimilating the high resolution chlorophyll observations into the biogeochemical model to generate analyzed fields of chlorophyll. And the process studies, one recent example that I'm showing here is basically the changes in the surface salinity field that we can capture from satellite. This is one instance from SMAP, wherein we show how the salinity changes during the recent Tauktae cyclone in the Arabian Sea. So one can see that before and after the passage of cyclone, there was an increase in the sea surface salinity, as you can see in all along the coast of the western coast of the Indian region. So these were some of the applications that we do. And coming on to the future, so we know that the current generation of altimeter that basically gives the sea level at a 25-kilometer resolution. However, the future SWAT mission from ISRO CNES we will be able to get the synoptic coverage of high resolution dynamic topography of the ocean. So here I am showing one instance of the current status of the observations available from altimeter, which are at very coarse resolution. And on the right hand side, I am showing the simulated observations from a SWAT simulator, which is basically showing the very fine details that we will be getting in the near future. Similarly, the OceanSat-3 mission, that's an in-house mission, will be providing very high resolution of ocean color, ocean surface temperature, and wind vector, basically all simultaneously from a single platform. So these will be available in the next 1 year time frame. Then we will be having the INSAT follow-on mission, which will be giving various geophysical parameters. SWAT, as I mentioned just above, that it's a wide swath altimetric concept for high resolution ocean and land hydrology study. As you can see from the figure in right, basically the SWAT sensor will be able to capture very high spatial scale of sea level variability and very near to the up to very near to the coast. Now currently the observations that we get from altimeter, there is a gap from the coast of around 25 kilometers, but with the SWAT mission we will be able to go very near to the coast. And with these observations and in synergy with the high resolution model, we can aim to get very high resolution coastal sea level observations as well. So we'll be basically aiming in future to make a synergistic use of very high resolution imagery of sea level and ocean tracers, along with advanced data assimilation techniques to improve the flow for process studies by means of image assimilation, and also to develop techniques for projecting sea level near to the coast. So this was a glimpse of what we have been doing currently and what we will be doing in the near future. So thanks a lot for your attention. Thank you very much.
Thank you, Neeraj, for that informative talk on satellite measurements. So I think since we have already gone, we'll be on the scheduled time. We can conclude the meeting today, and we continue at 8:30 p.m. Indian Standard Time tomorrow, and then we will organize discussions via email in the next few days before we meet again on September 13th, the Monday. So thanks for all the speakers and the rest of the audience who stayed up late. Thank you very much, and we'll continue tomorrow at 8:30 p.m. Indian time. Thank you.
Thank you, Mani.
Thank you, Mani.
Thank you, everybody.
Thanks, Mani.
Thank you.